let's see, there I am over there. New Horizons has been going for a while. We launched back in 2006, and just to remind everybody, let's see if we can get this to work.
2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit Pluto and then beyond.
So this is what it looked like. And it was a beautiful launch, and it's actually one of the faster launches off the surface, if you've ever been to a launch.
As the atmospheric vehicle climbs away from Florida's east coast, the 5-star rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
So, you know, the interesting thing about that, of course, is it was the fastest launch from the surface. We are, right now, we are going to be going by Pluto at about 13 kilometers a second. Of course, when we launched, we got from the Earth to the orbit of the Moon in about 9.5 hours, as compared to about 3 days for the Apollo astronauts. But we are slowing down as we continue to climb out of the Sun's gravity field. And so New Horizons, although it was the fastest launch, it's not the fastest object. Voyager 1 still actually holds the speed record on that one, and I'll talk a little bit more about that as we go forward. So I always like to put a little bit of history into all of this, and New Horizons didn't just start back in 2006. It actually started back in 1988-89, which was when Pluto was at perihelion for the last time on September the 5th, and this was a flyer from a cookout that Alan Stern, who's the principal investigator on New Horizons, had put together at the University of Colorado when he was a graduate student at the time. And then next to that is a special issue of one of the journals that came out that Alan actually had organized. And so this was before there was anything called New Horizons, anything called the New Frontiers program. It was just, and it was also before there was any debate about whether Pluto was really still a planet or not. And but there was a group of us that thought that this was a reasonable thing to do. So one of the things that you have to have in this business, of course, is a lot of patience, and the point really being that these things really do not happen overnight. And of course, one of the big issues about Pluto has been that you really can't see it that well here from the Earth. This is, I think this is kind of a comparison because you know, we've been taking pictures, of course, of Hubble here for a while, and that shows Pluto at the best Hubble resolution, and that's the Earth's moon at the same resolution. Okay, to put a little bit of this into context, and then of course that's what the moon looks like if I look at it with at least some sort of decent optical apparatus, and we're going to be doing that and a lot better at Pluto once we get there with New Horizons. And that's the point. I mean, once that you actually are able to take a close-up view of these various objects in our solar system, all of a sudden you're rewriting the textbooks because it really is a new window on the world. And that's the 5 kilometers per pixel. So, of course, this whole idea was to not only just look at Pluto with New Horizons, but also look at this new part of the solar system, the whole idea about the solar system's third zone, where the Kuiper Belt objects are. And of course, the launch was back in January of 2006. We flew by Jupiter. We're going to be coming up on Pluto and Charon, of course, in another couple of years. And then we've still got a mission going on out to the Kuiper Belt objects and beyond as well, because we're going to have a functioning spacecraft. And of course, there's a lot of stuff. There's a lot more stuff to be found out in the outer part of the solar system as well. And I just wanted to remind you what this thing looks like in terms of the size. It's not that big. That is the flight spacecraft as it was being assembled here at APL. And up in the corner is a little inset of one of the pictures of the plutonium-238 pellets. That's about an inch across and about an inch high. And that's the stuff that provides the electricity that keeps this thing going. And of course, it's a little bit like a battery that gradually winds down over a period of about 89 years. And the reason I wanted to mention this to you is, of course, this is the way that we power all of these spacecraft that go a long way from the sun. There has been a big debate in recent years about whether that the United States of America should be back in the business of making this stuff, because we had quit making it back in 1988. And unless we did something about it, all these missions like New Horizons to the outer part of the solar system were going to come to a grinding halt. And the good news is that over the last couple of years is that we've gotten back involved in the business. And so hopefully New Horizons will not be one of the last things going out there being able to run this. The New Horizons spacecraft and instruments and the science team, basically you're looking at the sort of 6 instruments, a few more sensors that all go together to do the science that we're going to be doing once we get out there. The science team has been together ever since that this was competitively bid back in the early 2000s, of course. And we're all still actively working on this, although we don't work on it all the time because nobody works on a mission all the time these days except for some of the engineering staff, just because we're trying to keep all of the cost in the box. I mean, it has been one of the interesting balancing acts, of course, as to how that one keeps going and keeps doing all of these things that we do on a limited budget. Now, the new solar system is, that part that we've learned about with these other objects that are out there. This is actually showing a sort of a blow up. You can kind of see, at the scale, the innermost orbit that's shown on there is Jupiter, which is of course 5 astronomical units out as compared to the Earth's 1 AU distance. So all the terrestrial planets can't even be seen on this. And we know that Pluto really is just the tip of the iceberg. Of course, the original discovery of the Kuiper Belt objects was with Hewitt and Liu back in the early 1990s, and since then we've been gradually piecing together this outermost area. And of course, the interesting object out here that's in the really large orbit, I think, is Sedna. This is actually the position of all of these various large Kbos about the current time. Sedna is not that far away from us at the moment. It's somewhere around 80 AU or so, but Sedna is in something like a 10,000-year orbit and actually goes out to 970 astronomical units, give or take a few, from the Sun. And so it's the largest thing that we actually know of that's gravitationally bound to the Sun, although, of course, we think that the long-period comets come from the so-called Oort cloud that extends even further away from the solar system. And so again, just pointing out Pluto and Eris, of course, is the other object out there that was discovered that led to the discussion of what really constitutes a planet. At the moment, it looks like that Eris is now back to being a little bit smaller than Pluto, so we're still arguing about that, and again, pointing back to Sedna. This is what happens the view you get if you look at the edge, and of course, what you see here with all the little yellow dots, these are sort of most of the objects that are out there, and you can see that all of the planets pretty much line up in one plane, the plane of the ecliptic, which is where the orbit of the Earth is. And of course, this is just a question of the angular momentum of the solar system and how that the solar nebula condensed a long time ago. What's interesting to note is that some of these other objects, such as Eris and Sedna, are actually in these orbits that are fairly highly inclined to the plane of the ecliptic. And so that's telling us something that we haven't really thoroughly been able to digest yet about exactly how that the solar system came together a long time ago. One of the things, of course, that's been going on and since that as things have been moving is trying to go ahead and take Hubble images of Pluto. These are some that were taken originally, including some back in 1994, some in 2002 and 2003. This was work that Mark Bowie and his colleagues did back in 2010 and published. And of course, the idea is that there are these very slight variations. And so we're using that to kind of eke out an idea of what the Pluto might actually look like. And again, this goes back into a combination of actually planning for some of the image campaigns, as well as at least giving us an idea of some of the things that we might be wanting to try to concentrate on as we start getting closer and closer. And one of the things that Mark and his team was able to do is to actually use those and to try to get some idea of what the dark and light images pieces of Pluto might look like. And so what you're looking at are the various longitudes at the center of the projections as Pluto rotates on its axis once every 6.3 days. And there definitely are differences in the light and the dark areas. So something's going on. But in addition to that, Pluto's changing, and we know that now because as a result, partially of New Horizons, we've been able to get telescope time to be able to take a closer look at Pluto all of the time. And the surface is certainly getting slightly redder and slightly brighter. There's sort of 10% effects that are running around. And Pluto's atmosphere has actually been getting a bit thicker. And this is something that we're all quite interested in. I'm very interested in it because I've got one of the instruments that's hopefully going to be able to remotely sense how much of the atmosphere may be blowing off into near space. One of the things that we had really been concerned about back in 1989 when we were all thinking about this and going, well, and of course part of what spurred this was that was just after the time that Pluto's atmosphere had been discovered from a stellar occultation, and we were going, well, it's moving further from the sun, it's cooling off. So that means that the atmosphere might condense out. Gee, we better get a mission up there soon before the atmosphere disappears. And it's been a concern, but it turns out it has not been a well-placed one because as there have been more occultations where we've been able to remotely monitor the atmosphere, we found that it's still there, and actually for a while it was increasing, and we should be able to have something that's going to be very intriguing scientifically and tell us a lot about what's going on with this Kuiper Belt object once we actually get there. Now, of course, the other thing that's been happening is that, again, partially because of the motivation of the New Horizons mission, we've been looking at the Pluto system very carefully, and we started finding more moons. And so, of course, Nix and Hydra were discovered. Charon, of course, was discovered back in 1978 by Christie and Harrington. And you can see Pluto in the center here. We can see Charon on the side, and then you can see Nix and Hydra that were the next two. And then P4 was discovered in 2005, and we've kept looking, and P5 was then discovered back in 2012. And again, what you're looking at here, these are photographs from some of the best seen from the Hubble Space Telescope that have enabled us to actually see Pluto in these worlds. And once that we actually get there with New Horizons, of course, all of a sudden these bright dots of light are going to become worlds in and of themselves. Now, after we launched New Horizons, of course, the only other planet we've been by is Jupiter. That was actually about 13 months after launch. We used Jupiter as a gravity assist. But the other thing that was important about Jupiter was it enabled us to turn all of the instruments on the spacecraft and actually gave us a chance to do calibration of all of the instruments in the space environment. I mean, one of the things that you do anytime you build a spacecraft and put instruments together is you worry about, well, are these things going to really work the way that you designed them to? And you do everything you can with thermal vacuum chambers and with various calibrated light sources and with ion accelerators and dust accelerators and whatever to try to test as much as you can. But at some point, you just simply cannot replicate the full-up interplanetary environment on the surface of the Earth, even if you pulled out all the stops with your best vacuum chamber. It's just not going to happen. You're always going to have, at the very least, edge effects that you can't get rid of. So one of the things that's very helpful is to have a planet on your way there that you can actually turn your instruments on and take a look at. We did that with New Horizons. Everything worked incredibly well. The little inset that if you've been looking at this on the left-hand side of the screen, you can see the little motion that's going on up there. That actually is one of EO's volcanoes erupting. That's a film loop that was taken with the Laurel camera on board New Horizons. And yeah, EO really looks like that, and it really does have volcanoes, and the darn things really do erupt. And of course, this was one of the big discoveries that came out of the Voyager program. And so we've only known about these things since 1979, and it's made EO one of those worlds of interest in and of itself. Pluto closest approach encounter operations will begin in 2015. We'll be starting to think about, well, we're thinking a lot about what's going on right now. There will be some initial operations after we come out of our final hibernation toward the end of 2014. The operations for the closest approach start in April of 2015, and right now the closest approach is scheduled for 14 July 2015, 11:49:59 UTC plus or minus a few milliseconds. Now, the real question is not when that we've got the spacecraft clock and the sequences set for doing closest approach, But the real question is knowing exactly when closest approach is going to be, because we don't know where Pluto is that well. It's an interesting problem that has come up in this mission, and it's one that we continue to work, because if you think about it, it's over 280 years that it takes for Pluto to go around the sun once. The first discovery, of course, was by Clyde Tombaugh back at the Lowell Observatory in 1930. There were apparently a few plates that we found that have Pluto on them that predated that. It's not surprising. Apparently Galileo actually had a sighting of Neptune that he didn't realize at the time, before it was really recognized by Adams and Leverrier in the 1840s. And so one of the things we've been doing is on the New Horizons team, not me, but the people that worry about the photons, is to try to understand, well, okay, so if I go back through all of the records that I have of the best astronomical observatories, how well can I nail Pluto's orbit? I mean, I can look on the sky, and so I know, looking out, what the right ascension and the declination of Pluto will be, and so I can tell in a two-dimensional sense where it is. What I don't know that well is how far away that Pluto is from the sun. And so we're working that actively. One of the things that had to be built into all of the sequences that we're using for imaging, that we're using for looking at the upper atmosphere, is to be sure that we don't just look at where we think that the planet is going to be, but we also look around in the area of space around the planet where that it might be if we're off on our orbit calculations a little bit. Because it would be a very, very bad day for a very large number of people if we flew by Pluto and we pointed the camera in the wrong direction. So these are the sorts of things that one worries about and has to worry about in the real world in taking a look at where stuff is. I mean, like I say, we can nail the position of the spacecraft very, very well because of looking at the Doppler residuals from the carrier beacon that's on board, with us being in radio communication with the spacecraft. And so we know where everything is except for knowing exactly how far that Pluto is from the sun, which is sort of an interesting problem. And I can tell you that when we first started writing the proposal, it was not one that was up at the forefront of everybody's thoughts. Just to give you an idea about the instruments, though, they certainly are all go. What we do is we have these periods where that mostly we're in hibernation. That was done to save mission operations money, and so we get every week we get a green tone or a red tone, and basically that's a coding for what we get on the radio carrier. Green means we're okay. It means I'm okay. Are you okay? Coming from the spacecraft. A red tone, which we've gotten occasionally, has been the spacecraft saying, help, somebody needs to help me, I've got an issue. And those issues have been things that we've been able to resolve quite easily from the ground, and we've taken care of that. We've been doing, in addition to the flyby imaging back at Jupiter when we went by, we've actually been exercising some of the instruments at other times as well. For example, right now, the two particle instruments, one of which that I'm in charge of, have been actually running during the hibernation periods of cruise, gathering data when we're out of contact of the Earth, and then being able to broadcast that data back down when we come out of hibernation for the yearly contacts back with the Earth to check out how well the spacecraft is working. And everything has been going swimmingly well. The picture that's on here is actually from one of those periods where that we were actually operating Laurel. Again, this is the long-range imager, and that's looking back at Jupiter, and it also shows Ganymede and Europa, and they're pretty smeared out there. Well, you're looking at them from 16.3 AU away. So if you think about that, the distance of Pluto looking back at the Jupiter system was greater than the current distance of the Earth is from Saturn. And yet we were able to see it. At the same time, there's another picture here I haven't shown where we were looking forward and looking out at Neptune. We've actually, with the instruments on board New Horizons, we've actually been taking pictures of Pluto as well. So we can already see the target that we'll be running out to. Putting together the encounter operations has been a huge, huge effort. It's very typical of what was done in a way back going to the earlier days of the space program, where that Originally we did flybys because the flyby was easy. Getting into orbit is a lot harder. Some people have said, well, why aren't you going into orbit around Pluto? Well, we're going to be going too fast. I mean, the interesting problem with the outer part of the solar system is that if you want to go slowly enough so that you can easily get into orbit with the kind of rocket engine that you can carry, it would take you decades to get there. If, on the other hand, you want to go fast enough that you can get there in a reasonable amount of time, there's no way that you can carry a rocket engine that is sufficiently powerful to enable you to break into orbit. You're simply going too fast. And so that's the reason that the first thing that we've always done have been flybys of the various planets. Voyager, of course, which is still operating out there, launched back in 1977. Both of those spacecraft, of course, flew by Jupiter and Saturn, Voyager 2 making the first flybys of Uranus and Neptune. They were indeed all flybys, because if you were going to try to get the speed up enough to be able to do the so-called grand tour of the planets, there's no way you could slow down enough to actually be captured by the gravitational fields. And so that's why that New Horizons is a flyby mission, and that's why that the first time we've gone out to enter any planetary bodies, that those first missions have indeed been flybys. Just to give you an idea of how fast we're moving, of course, Pluto is about 1,125 kilometers in radius. I mean, that's around the current best number that we have for that. And if you look on here, you can kind of see that's about the size of Pluto to scale on this. And you can see the numbered tick marks are hours. All right, we go through closest approach, which is really, really closest approach, pretty rapidly through the system. Now again, we're going to be actually starting to take pictures that are going to be better than the resolution of the Hubble Space Telescope in April. And this is what you're seeing on here is all going on within the space of less than half a day on July the 14th of 2015. There are a lot of critical events on here. You can see one of the things, of course, we're trying to do is to actually be able to fly through the occultation zones of Pluto and Charon with respect to the Earth. We'll be having the radio science experiment turned on with the idea that as we go into occultation, we'll be actually able to use the radio science experiment to be able to look for very slight changes in the carrier frequency, and from that be able to deduce the vertical structure of the atmosphere and to be able to look for an atmosphere of Charon. To say the least, it is a precise bit of timing that one has to put into all of this. What's not shown up on this slide are all of the other observations that we've got. We have a 3-axis stabilized spacecraft, unlike Voyager, for example, that had a gimbaled platform that had the camera on board. But gimbal platforms cost a lot of money. You have to test them out, and so it's actually cheaper to be able to build a spacecraft where you move the whole spacecraft with the little rockets that are on board rather than moving a scan platform. And so that was what was done here, because this is a low-cost mission. I still couldn't pay for it out of my checking account, but it is still a low-cost mission compared to some of these other things that we've flown. And so what you don't see on here is that one of the things that we're going to be doing, again, is scanning throughout the Pluto system. We're going to be making mosaics, because we don't just see all of Pluto in one particular frame, but we'll be down to the point where we'll have multiple frames to cover the planet. But again, because of the uncertainties and knowing exactly where the Pluto is, we will have to oversample those regions as well. And all of that is built into the sequencing. The sequencing is something that's done by hand. It's checked and double-checked and triple-checked, and I think we've been up to about 10 times checked on some of these at this point, and typically with all of the activities nailed down to the nearest millisecond over a period of several months. So a lot goes into this. It's not just simply like, oh, by the way, let's fly by, because if we screw up, we can do it again. Doesn't work that way. So, this is one of those things where when they say you better get it right the first time, it's a real serious business. And this just gives you a little bit of better of an idea of some of the details of what one of the closest approach timelines look like. So, for example, if I look up at the top, I've got Pluto global pan maps at 0.9 kilometers per pixel. Charon global pan maps at 0.9 kilometers per pixel. Pluto global IR at 9 kilometers per pixel. NExT is, of course, one of the satellites. Global color maps at 2 kilometers per pixel, and so on. And again, this is just sort of the next level down. There are more levels down underneath this. And one of the other things, of course, that's been going on is as we have gotten closer, and because of the fact that we do have had the support of a lot of the rest of NASA and have had support of the people over at the Space Telescope Science Institute, we've got a little bit of a better notion of what the Pluto system looks like, and indeed we have these other satellites. And one of the things that we have had some concerns about is, okay, if you have satellites, well, typically you might or might not have some dust rings in the system. You think about Saturn, for example, which indeed does have dust rings. You think about Jupiter, which in close has some dust rings that are associated with some of the satellites. And what you want to be sure that you don't do is that you run into a dust particle that is so big that you do something really bad to the spacecraft. And so there's actually been a lot of concentration that has been going on about to what extent that we should perhaps tweak the trajectory somewhat. There are, for example, there are clear zones that you can get from gravitational analysis of where the Charon is in the system that would perhaps be better to fly through in that region than it would be for the first nominal trajectory that we had. And so every time that you go back through and you get more information about the system in order to reduce the risk that we might have a problem, well, then you have to tweak the timeline. And when you tweak the timeline, everything cascades through. So we've actually the operations team and the science team together have built several of these. There's at least, I believe there's another activity that's going on now, and I think there's going to be another activity coming up as well, so that again we've got the appropriate options to be able to carry this mission off and make it the success that it needs to be. And some of the observations that we will actually need in order to make sure that we know exactly what we're flying through, a combination of being able to look for hazards that might be there, as well as getting better and better updates on exactly how far away Pluto is from the spacecraft, will be coming in during the weeks before closest approach. And indeed, there is a period where that we've got sort of a last opportunity to be able to fire the rocket jets and do some final tweaks into exactly how that we are going to be going through the system. And you have to also worry about the fact that we're something like, if I remember correctly, about 4 light hours out at this point. And so you can't just say, hey, use spacecraft turn, and then have it turn, and then find out that it turned. So all of that also has to be taken into account. And of course, when you move things a little bit, that throws all of your pointing off. So you have to make sure that you haven't done something outside of the bounds of what was already planned with respect to where we're going to be pointing the camera. So, and I'm just barely scratching the tip of the iceberg here about how complicated that this has been in terms of trying to make sure that we have an absolutely successful mission. At closest approach in 2015, the southern hemisphere is going to be sunlit. The dark part is going to be at the northern polar cap, and we're going to be approaching from the south. So this gives an idea of sort of what that it might look like with a sketch of what maybe Pluto could appear as. I checked on the website today, and there is a website. If you're interested, you should check. So as of today, and if I did the right calculations on numbers as of approximately right now, we are 25.87 AU from the Earth. So that's a little more than 3.5 light hours out. Mission elapsed time is 2,633 days and 23 hours, give or take a few minutes. And our closest approach time to Pluto, we're now down to 828 days and 18 hours. And these clocks have all been running on the website ever since that we launched the spacecraft. And again, I would urge you to, at least ever so often, drop in on the website, take a look, and keep up with where we are. And then, of course, what I wanted to end with is just say a little bit about, well, what's next? Because, of course, we've got a good, healthy spacecraft. It's not going to end. The mission's not going to end, budget's willing. after we fly by Pluto. Right now, it's going to take, in order to get all of the data down, probably something, if we stay on the 34-meter DSN, something on the order of 9 months to play all of the data back from the encounter, because it's a long way out there. But then after that, we're going to be looking for another Kuiper Belt object to fly by. We haven't quite found one within the propulsive capability of the spacecraft yet. But the other disadvantage we've had is we've been looking at with the background of the Sagittarius star field, and we're going to have which gives us a terrible background to be looking for very, very dim objects, and we're going to be coming out of that sometime soon. We're continuing to look. We should be able to find another object that we can get by. And indeed, if you look at the RTG power on board, again, our little plutonium battery, that is gradually running down, but we're good to go until about July of 2032 in terms of power, and that would take us out to at least 84 astronomical units and enable us to join the heliospheric fleet of the other spacecraft, all made in America, by the way, that are actually on escape trajectories from the solar system. Pioneer 10 and 11, of course, launched back in 72 and 73 are dead and offline. Voyager 1 and Voyager 2 still sending back data every day. The little spacecraft that could, we get back something like 100 bits a second from Voyager 1, 5 days a week, and typically about 6 to 8 hours a day. We're looking now at the edge of the solar system near where the heliopause, so-called heliopause, is and interstellar space starts. And right now, Voyager 1 is at about 122 AU out, so that's about 4 times as far away from the Sun as Pluto will be at the New Horizon encounter. But nonetheless, it's a grand opening out there of having new science coming in, looking from the outer parts of the solar system, and New Horizons is going to be playing a major role in that. And so stay tuned, and in a couple of years, we're going to start rewriting all the textbooks. Thank you.
Does anybody have any questions here from APL?
Yes.
When, I know you've given us sort of an idea of when closest approach would be, but when can we expect to sort of see some of the first observations from Pluto?
Well, the idea, of course, is that we're going to be making this stuff available as rapidly as we possibly can. And you know, I haven't talked to Alan Stern recently about this, but my guess is that we will probably be trying to get something out pretty much on a daily basis, with having at least some of the stuff coming down. Now you have to keep in mind that again we do have you got to worry about how fast we can get the bits back, and so you know you don't run this stuff real time. You can't do that, and so I'm not sure. Actually, I don't know right off the top of my head exactly how long it takes us to get a full image down. It does take a while. It takes us the 4 hours or so, along with whatever that the bit rate is. But rest assured, we are going to be putting stuff up as fast as we can. Right now, the way that the very closest approach is scheduled is to be sure that we get some quick view products back for the science team, which will be coming out, as well as all of the detailed science data, which will be, for the most part, loaded on the recorder, simply because we don't have the bandwidth, and that's what's going to take the 9 months to get back. So there is going to be some latency there, but we'll be getting stuff back as fast as we can, because we're as excited about seeing this stuff as you guys are, and indeed we're also excited about getting all of this knowledge and all of the results of this investment out to everybody. Yes, sir.
You mentioned that the Pluto atmosphere is becoming thicker, but it is not denser, is it?
Well, that's a good question. I mean, one of the things that we don't have a really good idea of is exactly what's going on with the atmosphere, which is why that several of the investigations are going to be taking a look at that. We don't have good models right now for saying why that the atmosphere should be varying as it is. Our best guess is that the atmosphere is probably a combination of nitrogen and methane, but we don't even know that for sure. So your question actually relates to something that we're hoping that we're going to be able to figure out once we get there. We know that there's something there that is certainly there's more of it because of looking at the extent of the occultation and how far away that is from the planet and what the slope of the occultation curve looks like. And we've all got our fingers crossed that this behavior is going to continue going on and it's not going to freeze out in the next 2 years. But who knows?
A follow-up question, if I may. You also mentioned about the pointing camera, and it's very difficult to know where Pluto is when our spacecraft goes there. But there's quite a lot of optical guiding systems as well as gravitational attraction systems that could be used to point the spacecraft.
Well, right now, I mean, we're pretty much on. We've got a good inertial guidance system that is on board. We're doing, of course, the tracking with the Doppler tracking with the DSN. We do also have star cameras on board, and so what we can do is we can look against the star field, and that's really the main way that we know where we're going and where we are at a given time. A combination of all of those things together. Had another.
We have to.
All right.
3 other sites.
Yes, ma'am.
Sorry. I want you to ask him afterwards. I believe we're going to JPL next for a quick question.
Yes, we are.
Hi, when New Horizons is at perihelion, how is he going to get sharp images of the planet? Because it's going to be going by so quickly. What type of optics are they going to do to correct for the blurring, if you will?
Well, actually, it turns out we don't go so close that we end up blurring. It's, I mean, you note a very important thing that on a lot of these missions, one has had to deal with image motion compensation. It turns out that with the cameras we've got on board and the distance that we're coming into Pluto, that we can actually take the pictures fast enough with a fast enough exposure time in the dim light that we still don't have a dimming issue. And that, of course, has been something we've been planning on for several years now, and we've got all of that nailed down.
Thank you. I believe we're going to
University of Arizona. Does the University of Arizona have a question for Ralph McNutt?
Yes, ma'am.
When you the confusion about what the possible distance from the sun would be, and when you started this project, what was your estimated distance that Pluto would be from the sun when you get there, and how has that changed based on the information you've gathered from this mission and from other sources?
Well, we're gradually working on this. When I say we don't know how far that Pluto is away from the sun, here's the issue that at least as of the last science team meeting we had, we were still looking at an error in the arrival time of about 100 seconds. So we know pretty well where it is. We just don't know exactly where it is. And so again, what we're going to be doing as we continue to go forward is that we're researching the old archival records, looking at some of the old photographic plates to try to get a better idea of the orbit. And then as we start to, and like I say, basically being very prudent in how that we're putting together backup imaging plans, as well as we get closer and closer to the system, we will have some opportunities to tweak things a little bit. So there are several levels of planning that are actually going on right now to make sure that we actually get Pluto in our sights.
Thank you. And last but not least, Johnson. Any questions?
Yeah. Can you explain what clear zone is?
Yeah, it turns out that because of the complicated gravitational potential of both Charon and Pluto and the moons, but mostly Pluto and Charon, there are regions where that dust will tend to accumulate or could tend to accumulate, and regions where the dust tends to be repelled. Sort of a simplified version, of course, if you think about the L4 and L5 Lagrangian points for the Sun-Jupiter system, we know that there's an accumulation of asteroids at L4 and L5 just simply because those are where there are minima in the gravitational potential. Well, the Pluto system's a bit more complicated, and dust is a little more complicated than asteroids as well, and you have to worry about a lot of other dynamic effects. But there are regions in the system where that the dust to the extent that there is dust there, it should be pretty minimal, and so one of the things that we're looking at is flying through that region, and that would help to mitigate a lot of the worries that have been expressed.
Okay, I'd like to thank Dr. McNutt.
Thank you.
Alrighty, so we're a little bit behind. We have activity here at all sites, icy worlds, investigating icy worlds. I have a colleague on the Dawn mission who said 2015, when we arrive at Pluto and we arrive at Ceres in the main asteroid belt, could be a deal breaker in terms of a lot of our concepts for the origins of the solar system. So it's a very exciting time. So to get you all jazzed up for that, we have an activity, icy worlds. So let's say we are going to reconvene at 5 minutes till. So let's give 10 minutes so we have enough time for that activity. I think we've got a little flex time later in the day. So we will reconvene at all sites let's see, for us it will be 12:55, Arizona 12:55, Johnson 2:55, and at APL 3:55, and that will be at APL starring the messenger mission. So thank you so much, and we'll see you again about a half an hour, 25 minutes.